So now we're going to have a brief overview of how you can use different kinds of performance tools to find the problems in your code and also help you guide understanding how to fix those problems. There is a whole bunch of performance tools out there, many free tools that's been developed in research organizations or sometimes in companies. So we have OProfile, we have gprof, coupled to the GNU organization. AMD has the Code Analyst, Google has some performance tool, and there's a virtual institute for high performance productivity for supercomputing that also publish their tools. They are mostly targeting supercomputer tools, of course, or architectures. There are also some number of commercial tools. So Intel has a very popular tool called Vtune and many other performance tools, but specifically looking at cache optimization, Vtune would be the one to look for here. HP has put together what they call the multi-core toolkit, where they group lots of tools, some of them open tools and some of them commercial tools. And we also have, amongst other commercial tools, the ThreadSpotter tool that we developed in my startup company, Acumen, and it's now marketed by RogueWave. And should highlight as well that I have no longer any kind of economical interests in this, but of course, this is the tool that I will also present in this lecture. So first look at Vtune. So Vtune is what I call a broad spectrum low-level tool. It helps you find lots of different problems, not just cache-related problems. It's a low-level tool in that it presents statistics about specific hardware units and hardware events and let you yourself try to figure out what the problem is. So you can, for example, use it for profiling. So it will tell you where you spend your code, where you spend your time, in which part of the code you spend most of your time, which function, and so on. And it also gives you hardware counter-based information. So it will tell you for the CPI, for example, it can tell you instruction misses, data L1 misses, L2, L3 misses in your caches, in your TLBs. It can tell you how well your branch predictor is doing. And this data can be divided up and be presented for the entire application per function and even down to each instruction level. So very detailed, very hardware-focused information. So it often requires hardware architecture knowledge to understand the statistics presented by Vtune. But since you all are taking this course, I think it should be fairly straightforward for you to use this tool. I should also say that Vtune, if you're interested in using this, they have evaluation licenses. That's valid for 30 days. So you can just download this tool and get it up and going on your system. Here's an example of the low-level information you will get. And this is divided at the macroscopic level, at the system level, where you're spending your time and so on. You can, inside an application, understand where you spend your time, how the different levels in the what functions call what other functions. You can click on one of these functions and you can get specific information about who it's calling, or you can also get statistics about that function. You can get also views over time what is happening at the macroscopic level as well as in the architecture level. So you can see how the L2 cache misses go up and down and so on. So this is detailed information and very accurate information, and it's a mature tool that lets you focus in on, most of all, focus in on the functions where you have your problems, and then you will have to stare at those functions yourselves and figure out how to fix them. I said that Vtune is based on hardware counters, or more specifically on programmable hardware counters. So in modern processors, typically the hardware architects have implemented some number of hardware counters, and they are programmable, and in that they can be told to count certain events. So one hardware counter can be told to count cache hits, the The other hardware counter can be told to count cache misses, and by looking at the numbers that comes out of those two counter values, you can figure out what the miss rate is in your cache. But also you can count specific stall cycles in the CPU. So you can, for example, count how many stall cycles do I have in my CPU because I have data dependencies, and how many stall cycles do I have because of the wrong branch predictions being taken and so on. So very, very detailed information. It also, if you use hardware counters, then your tool will run at near native speed because these are built-in counters. It only inserts extra runtime overhead whenever you need to go and read these counters. So if you need to break down the counter information at an instruction level, that means you will have to go and read these counters more often. But still, typically these kind of tools runs at near native speed. The tool that we developed could more be characterized as a cache tool for dummies. It's not broad spectrum in that we only look at different cache-related problems. And it's for dummies in that we don't require you to have detailed knowledge about computer architecture, that rather we teach you as you go along. So you take your application just as in Vtune that's been compiled by any compiler, and you run your binary. But instead of us counting or looking at specific hardware counter information, we have implemented our own sampler technology that sparsely will measure the application's locality. So we measure some locality properties of the application and gather that all into what we call a fingerprint file that, regardless of the running length, typically end up being about 4 megabytes large. And then we use some offline analysis where when you do the analysis, you tell us what the properties of your target system looks like, what cache sizes you have, and so what cache hierarchies you have, and so on. And this could be the same as the system where you capture the information, the host system, or it could be some other system you would like to do the analysis of. And this is all this sampler and analysis is based on the technology we have developed earlier in our research group. Then we tagged on a heuristic level, an advice level, that not just figure out how the application is treated by the cache hierarchy, but also try to find places in the code of the binary where we think that it is an opportunity for improvement. So we present this, what we present to the programmer, to the dummy, a list of performance problems. So what problems do you have? And you may be able to read here inefficient loop nesting, loop fusion, poor utilization, and so on. So these are issues that we already discussed in this course. You click on one of them and we take you to where in the code that problem is. And we also have a window that tells you how to fix it. And if you're a real dummy, there are lots of question marks you can push everywhere, and we will have some context-sensitive manual that will tell you, for example, what it means to be walking in a data structure in the wrong dimension if you do column-wise instead of row-wise. So you don't have to take this course first in order for you to be able to use this tool. Here's an example of the kind of performance problems we can find. So in this specific application, with poor utilization was the worst problem. With respect to how bandwidth is used, there are other tabs that will focus on latency issues. It tell you what loops are doing good and bad. We're looking at coherence activities and so on. But for latency issues, poor utilization is the worst problem, loop fusion is the second worst, and so on. So we have the list of bandwidth slow spots. We have a place where you can spot the crime, and we have a window explaining how to go about fixing the problem. We also show you lots of these graphs. So this graph here we already looked at when we looked at some of the possible software optimizations. This graph is often referred to as the nerd curve, because typically you have to be cache nerds like myself, and what you are almost becoming to be yourself right now to appreciate this curve. It, for example, shows you the miss ratio for an application as a function of cache size. It shows you the fetch ratio So this corresponds to how often you have to bring things from the next level in the cache hierarchy. So that implies this would have been the miss ratio and the fetch ratio would have been identical if you had no hardware prefetching in the system. But now, obviously, for this application, the hardware prefetcher is doing a pretty good job here. It also shows you fetch utilization, which is the fraction of the fetched data, cache data, that was ever used before eviction. So it more or less tells you how effectively you are using all the words of a cache line. If you only use one word of the cache line, you will have a low utilization number. So that's the blue line, and you read the utilization on the right-hand side. We also show you, tease you a little bit and say, this is the fetch ratio if you fix your utilization problems, because of course you want the utilization to be at 100%. If you did so, this curve up here would actually change to be all the way down there. So we're going to look at a specific example. This is from the Spec Benchmark Suite 2006. It's called LibQuantum. It's developed by some German researchers. It's a neural net quantum computer simulator, and 4,000 lines of code, and it takes about 30 minutes to natively run the one experiment using this piece of code. And we run it on 1 core. We run 2 instances of the same application, 2 cores, 3 cores, and 4 cores, and you can see that it does level off. So we can expect there is some bandwidth problem, memory bandwidth problem, because it doesn't help you much to start to use more cores. So we take a little demo. We're going to start up the tool, and we can see at the first screen that looks like we are having memory problems, a little bit of latency problems, huge amount of data locality problems in this application, single thread. So it's a single-threaded application. We open the report, and the report once more this is focusing on bandwidth issues. That's all we will do in this example. So we can see that the most severe problem is a fetch utilization problem. So it's how well you're utilizing the data of a cache line. We click on it. It takes you to the spot of the crime. So we can see what's going on here. Is that we are in this specific statement in the yellow frame here. We are looking at we have a vector, and that vector is a vector of structs, and we have one specific member of that struct, which is called state. And it looks like in this very important loop here, we are looking at just the member state over and over again. So you can see that's all what we do. We look at state, and we XOR some bits of that state given some specific condition of this code. We can also look at the node curve for the entire application, different aspects of the node curve, even more so than what I showed you in the previous picture. Or we can look at the node curve just for that specific problem that we were facing. So this is that specific problem here has a miss ratio of about 12.5%. So that should give you a hint. 12.5%, that corresponds to 1/8. So looking at that code again, so we have some piece of code here where we access just one member of a struct, and that should all tell you what's going on in this specific application. So this is what the overall curve looks like for this application. The fetch ratio is what you're going to focus on. The fetch utilization is at about 50%, and the predicted fetch ratio, if you fix it, it will get down to just over 2%. We can also see that if we like to have a decent fetch ratio, so a decent fetch ratio for this kind of architecture is right around just above 3% in order for it to run well, we will need a 32 megabyte cache for each thread, while what is target optimization has been done for an architecture where we have only 2 megabytes of cache per thread. So that's why you see this bar here. This is what the optimization heuristics has been targeting. We looked at the problem spot that we found. So we have some huge data structures, and it's a vector of structs, and we access only one member of that struct. So this is what it looks like. First, you have the status, some data value, some status value for the first member of the vector, and then you have the data value and some status value for the second vector. And these axes will go like this in this very popular loop. So my question to you is, what changes are needed for better cache usage here? Should we change the loop order, make a separate vector containing only the status variables, or should we change the stride to 8 bytes? Well, we should make one specific vector that only contains the status values, as we discussed in the optimization examples. So this is exactly the advice that ThreadSpotter gives you. And so you have to change, another way to say that you have to change your data structure to be a struct of vectors instead of a vector of structs. This involves about 20 lines of code, and it takes a non-expert that's never seen this 4,000 lines of code about 30 minutes to perform. If you make this change, my next question is, of course, what will happen to the nerd curve, to the fetch ratio? Ceiling come down, ski slope move left, or both. So both the ceiling will come down and the ski slope will move left. So this is the original code, and this is the utilization optimization that we just performed. And that's because after the fix now, each fetch will bring in more useful data into the cache, actually twice as more useful data. So this will probably come down exactly down to 50% of where it was before. And we can put the same amount of useful data, it would say all the status information that we're interested in, can fit in a smaller footprint. So that is why this ski slope moves to the left. We can also see that the cache utilization that used to be 50% now went to 100%. It's hard to see in this picture because the scale went off the slide edge here, but trust me that we are actually this is the 100% line up here, and we are right now at 50%. So let's see what this application looks like after we made the optimization. So now the bar says we still have a little bit of a memory problem. Compared to before, the problem has gone down, both the memory problem and the latency problem for this application. We open the report to see if there are still any problems to fix. And now we can see that we have lots of problems called hotspots. Hotspots are places where we see lots of cache misses, but we cannot see that you made any kind of performance mistake in your code. So the hotspots we won't be able to fix. But further down in the list, a little less important though, you see lots of loop fusions. So let's click on one of them and we can see loop fusion. So what does this loop fusion tell us? Well, it takes us actually to the same place in the code again. Okay, so with this loop that we just optimized, see this is a new data structure, underscore state instead of dot state, that can also be part of a loop fusion. In order to understand which loops to fuse, we can click on this, which will give you the fusible instructions for the first loop and for the second loop. So now if I click here, we will take it to the first loop that we can fuse and the second loop that we can fuse. This is a big surprise. I take you to the same line of code. Am I trying to tell you that you can make a loop fusion of this line with itself? Well, really what's happening here is you can see that this very popular loop here is part of a function called quantum topology. Okay, and if I click up so I can see the call stack to see where these instances of that I now tell you to fuse, where they were called from, you can see that the top one was called from line 151, and the next one was called from, the next instance was called from 152. So what my analysis says is these two function calls are actually doing pretty much the same loop, accessing a giant vector, and we know exactly which vector they are accessing, and all they do is they XORing a couple of bits there. So the advice is that you have to do a loop fusion. Of course, you can't fuse just trivially fuse different functions. You have to make a new fused version of the function. So this is, after we had the utilization optimization, and then the second advice said you have to fuse these several calls that all use some huge data structure, so that it just flips a few bits to some fused version of that function that will go through that vector once and flip the bits twice according to whatever this algorithm is. So it's a little more tricky. Actually, there are 4 advices that are exactly the same kind of advice. So here we would create 4 new fused functions. And this is a little more tricky. It takes a non-expert, which was myself in this case, 2 hours of tedious work to make that happen. But if you make that fusion, then the ceiling will come down. The ski slope will not move to the left because of the misses of the second loop that got fused. Those misses go away, so the temporal locality is better, and that's why the ceiling comes down. Still, we still need the same amount of data in the cache, so that's why the curve we saw after we did the utilization optimization, that curve does not move to the left, it just moves down when we do the utilization and the fusion optimization at the same time. So let's see what this application looks like now. So starting off from the first code, this is what it looked like. Lots of problem with memory bandwidth. Now we went down to less memory bandwidth, and the final code, we improved it a little bit, nothing dramatic. So comparing the original code, where we needed 32 megabytes per thread to get down in the 1% fetch ratio area, now we can get the same fetch ratio with only 2 megabytes of cache, and that was the goal of this optimization. From a performance point of view, this is what that means. So if you just look at single-threaded execution, we get a small improvement with a utilization optimization and a small improvement with the fusion. The reason we don't get more improvement when I go from, when to do the utilization optimization is that those cache misses would probably turn into cache hits. You remember we were fixing the bandwidth problem here. A hardware prefetcher will do almost a perfect job in bringing in the data. So if we had infinite amounts of hardware, you may not have seen any performance improvement here at all. So, but the more threads we run at the same time, the larger will the difference be between the unoptimized code and the fully optimized code. So for 4 threads, we see an improvement of 2.7%, 2.7 times 2.7x. So that's a decent for 2.5 hours optimization of a code that you've never seen before. That is actually a very, very good return. So you should ask yourself the question, shouldn't compilers do this job? Should programmers really care about this? And that's a very valid question. Answer is unfortunately that the world is broken. Of course compilers should do these kind of optimizations, and they are trying to do these optimizations. They are actually getting better and better at finding it. And specifically, if you give them a Mickey Mouse example, like some of the examples I gave you in the first lecture talking about optimizations, an optimizing compiler may be able to outsmart a bad programmer in those situations and correct it. But once that simple function is included in a more complex application, then it's going to be harder and harder for the compiler to figure out which of those optimizations are valid anymore. So for larger, more complex applications, unfortunately, even some of the simpler tricks will be missed by a compiler.